So I have a question from a student, Arnab Khatri, and he is a student of class 11th, and he writes, like charges on rest repel each other as a property, but the same charges during motion attract each other as a virtue of their magnetic fields. So what kind of force is existing between the two? Since it is well known that they would not come and stick together even though they are attracting. So that is the question. So it's a very nice question, and the discussions will also be very nice, and I am sure you will enjoy it. So let me start with two charges of same sign, Q1 and Q2. You have Q1 and Q2 at some separation and are at rest. So when you say they are at rest, you are using some frame of reference with respect to which they are at rest. So at rest in frame A, call it frame A, at certain instant, because they are repelling each other, so at certain instant they can be at rest, and after that they will of course go apart. So this is the situation in frame A, and the electric field at Q2 due to Q1 is, E is equal to Q1 divided by 4 pi epsilon naught r square, and in that radially outward direction, and the magnetic field is 0. They are at rest, so the magnetic field is 0. You have electric field, and then Q2 experiences force because of this electric field, Q2 multiplied by this E1. So that will be the force, which will be Q1 Q2 by 4 pi epsilon naught r square. Good. Now change your frame to frame B, which is going downward in this diagram, in this plane of the board. If I am drawing everything, it's going downward. So we are changing the frame. Again, what will happen to the charges? They will start moving with some velocity v. So you have now you have frame B. That was frame A. This is frame B. The picture is, you have Q1, you have Q2 going this way and going this way. That same instant, remember, instant, at that instant. Okay, so we have not disturbed the charges, we have not touched the charges, we have disturbed ourselves, we have gone from frame A to frame B. Nevertheless, particles are now going in the upward direction with velocity v. So what happens to electric field and magnetic field? As you change frames, velocities change. Frame A velocity was 0, frame B velocity is v. So velocities of the particles change when you change frame. Accelerations of the particle can also change if you change frames. Okay? Forces in the particles can change, positions of the particle can change, kinetic energy of the particle can change, many things can change when you change frames. Electric field and magnetic field also change when you change frames. So if it was E1 B1 in frame A, it will be E2 B2 in frame B. There are certain rules, certain relations, certain equations which will tell you that what will be E2 B2 if you know E1 B1 and your frame's velocity. So those rules are there, but they are relative. They are relative. In different frames, they will have different values. So here in this frame, you will have electric field, and so turns out, if I call this E1 B1 and this E2 B2, this E2 will be E2 at that place, it will be in this direction, and this E2 turns out to be very close to E1, which is 1 by 4 pi epsilon naught, and then Q1 by 4 pi epsilon naught r square, This one, very close. Unless you have very high relativistic speeds, for moderate speeds, for low speeds, this E2 is close to E1. What is B? B you can calculate. In fact, you can use Bad-Savart law or its equivalent. You can calculate. The field will be this B. If you remember Bad-Savart law, it is mu naught by 4 pi, then I dl cross r by r cube, something like this, and the magnitude turns out to be mu naught by 4 pi I dl sine theta, which is 1 here by r square. And for I dl, you don't have a current here, you don't have a wire here, you do not have a dl here, and therefore this I dl has to be replaced by its equivalent, and that equivalent is q times v. Okay, so with reasonably very good accuracy, you can write this as mu naught by 4 pi and then q times v divided by r square. Your sine theta is 1. Okay, the direction of magnetic field will be going into the board, and we are writing magnetic field here. So 90 degrees, sine theta is 1, so it is this. And in some direction we will write something. And this magnetic field will create a force on Q2 which is towards Q1, attractive. Magnetic force will be attractive. You can work it out, positive charges. Now, the whole game is governed by these two factors here. This factor is 9 into 10 power 9 in SI units. And this factor is 10 power minus 7 in SI units. Alright, so this 10 power minus 7 here, and this 9 into 10 power 9 here. Now you can see what is going to dominate. So finally they will have to repel and not attract. The electric force of repulsion is extremely high as compared to the magnetic force of attraction. So they will not come and stick to each other. They will indeed fly apart. Okay. So all these transformation equations of EB from one frame to other frame, velocities from one frame to other frame, these things are so consistent with each other that you get exactly the same predictions. You use frame A, you use frame B, you get exactly the same prediction of what is going to happen to these charges. Our nature is really beautiful, and laws of nature are still more beautiful.